Okay, so where this matrix tau is basically, so you just observe, you adjust in such a way that you get what you want. So tau xx. So what should I put it now? Nx, ny, nz. No, so tau xx, tau xy. This is our matrix, right? So tau xx, tau xy, tau xc, tau x, tau yx, tau yy, tau yc, tau zx, tau zy, tau z. Okay, and n cap is anyway equal to nx, ny, nz. So this is what finally you get. So this is important. Okay, so this is what we need. That's what. So your force is basically stress force is basically connected with stress matrix into n cap, your normal. Okay. So this matrix is basically, we want to show that this matrix is actually symmetric. That is your next step. Next step is this matrix tau is symmetric. This is another claim. This claim is this is symmetric. Symmetric matrix. So how do you show this one? This is where you have to use this what is called momentum, angular momentum. So how good you are to understand the angular momentum? There's a little bit physics involved, so you're a mathematics student, but still I try to explain you. See, you have angular momentum means what? See, this one, if you see, this is your R, and this is the angle you're just moving it like this, okay, in this direction, okay. So this is like a circle. You just think that it is a circle, okay. So you're just throwing, okay. This is your R, or you have object here, so you're just rotating, okay. This is a rotation. You're rotating, and you rotate it. Let us say this is your theta, okay. So initially at theta, once it after some time, it may be, let us say, in a unit time, in a time t, this becomes d theta by. So let's look at theta at t. Okay, so this is basically, if you connect it, this is your theta. Okay, this is your theta at t, and this whole thing is basically theta at t plus delta t. Okay, so when you do that, what is this one? This is your d theta by, right? So inside is simply, this is d theta by dt. Okay, or basically you say the unit time, what exactly? So consider delta t equal to 1. So when you do this, what exactly the angular what displacement? Angular displacement is what?
Is R d theta dt.
This is basically your this displacement, right?
Yes, sir.
This is the displacement, right? So angular displacement is actually equal to d theta. That is theta minus theta at t plus delta t minus, right? So theta at t plus delta t minus theta at t. So this is your angular displacement. Now, so implies angular velocity. What is angular velocity?
D theta by dt, sir.
D theta. So angular velocity is basically d theta by
dt.
But I think you will have not only that, this d theta by dt into r is also there, no? Is there any r into that? See, this is a straight line. This is angle theta, but you know the displacement we're asking, angular displacement, no? This is actually r into theta, right? This
Tangential
r d theta is basically that this is your angular this distance. This is your distance.
yes, sir.
Basically this into r. Okay. So d theta by so once you put this angular velocity, this into r. These are scalars. Okay. This is
Then
what
what is tangential velocity then?
tangential velocity of what?
This
These are rotations. No, we are doing the rotation. Angular. These are angular velocity. Rotation. If you actually see, you have to say exactly what is its displacement. What is from here to here? That is usual. This is the tangent. That is the tangent. That's an whatever the path you consider and take the tangent. That is what is usually you consider as a displacement. That's usual that you have seen. No, already. What is the path you consider? What is the derivative following the particle? You follow the particle. This particle, if you follow, wherever it goes, that's what happens. So when it is like when it is rotating, for example, that's what happens in the deformation, right? You have seen, no, in the fluid, it may rotate, it may displace, it may deform, it may rotate, right? So it's not the simple rotation. Everything is rotated here. So in the during because of this deformation, also there is some kind of rotation is taking place. Okay. So those are angular displacement, angular velocity. So once you have this angular velocity, and this is basically physics. You understand up to here? Yes.
sir.
So you say that v into theta, and this is like x into theta, x theta. Okay. So you're measuring in terms of theta. Okay. So this is x for this theta. Exactly what is your displacement? R into d theta. So r into d theta is actually your this thing. So effective displacement is this. Angular velocity is this. So actually you should say theta, right? Okay, so this is yeah, this is fine. So this minus this. From here to here, we are just checking angular displacement. Okay, the angular displacement for d theta we are calculating actually. Okay, we are just this is a notation x theta v theta. So you don't worry about x theta v theta. So anyway, this tells you that displacement. This is your angular velocity. There is r is also involved. Whatever this position vector r, no, the distance also matters. Now there is a principle F equal to ma that you have, no. This is your Newton's second law. What is the force here? So force in this is the usual way. Force equal to mass into acceleration. So equivalent thing in the rotation, the angular moment, angular case is force is basically it's called torque. Okay, torque is always perpendicular to what you have. So for example, if you consider only xy, okay, in the xy plane is your if your fluid element. So let's consider this as Tz equal to, that is your force. So Tz is actually torque. This is the force. Equivalent things I'm writing. So this is a torque force. Rotational dynamics basically. So mass, what is the mass actually? The mass, how it is, it comes as a moment of inertia. This mass, how it is moving along the throughout along the axis. That this is your axis, perpendicular to this point of your screen, basically your axis. So with that axis, exactly how mass is spreading round. Okay. So that is what is actually moment of mass becomes here moment of inertia. So I'll write it. I'll represent it as Iz. Moment of inertia. Okay, so this is your moment of inertia, and A is basically whatever you have seen, no, angular velocity. Now I want angular, what do you call this now? Angular velocity, I think you will not have R. Displacement only will have R. Okay, I think that's what. So you R gets cancelled here. So this you may not have here. You understand? Angular displacement is this. You can just think of, I think, Yeah, if you, I think there is no such thing, no? Angular velocity. Can you just check whether r theta or angular displacement r theta or simply d theta? Internet, can you just check angular velocity? I am not very sure with this physics. Angular displacement formula. Let me check it. So we'll confirm it. Just basic physics. Okay. Angular displacement is
Sir, r d theta.
r d theta only, no? Angular velocity. Yeah, r theta is basically. So angular velocity, let me check. Angular velocity. Angular velocity is basically, it goes
d
simply
theta by dt.
d theta by dt only. So yeah,
Yes, sir.
that's where is for some
Omega.
reason. Okay. So you understand from physics, okay, angular velocity will not have any r into it because the displacement is there, no? Exactly how much is displaced. But here we are finally taking the limit. So you will not have that r somehow gets cancelled. Okay. So you're only looking at theta, no? So as t goes to infinity, delta t goes to 0 only you're seeing. So finally that r will never come. So this is what is this one. So this is for basic physics. So you'll have, now you want basically, you don't want, here you want A is acceleration. You simply have, you say d square theta by dt square. This is your acceleration anyway. Angular acceleration. You understand? These are the equivalent versions. In the rotational dynamics, these are the things. Torque force is equal to moment of inertia, is like that. So now I can calculate what exactly my so now what is your fluid element that you are considering here in this case? When you are considering, you always consider, let me consider, not always, I'm considering here as a square. See, sometime back, just to get that quantity, where just to show this claim, we consider some small fluid element as delta A as a triangular element. Because finally, you are going to take it as very, very small, no? This is infinitesimal. So it doesn't matter whichever way. So you try to bring out this one. So here, if you consider this one, this is a square element in the xy plane. Okay. So this is in the xy plane. This is basically a cube in xy plane. Not cube. It's a cube basically cross section. This is the face of a cube in xy plane. Okay. So what are your stresses here? This is your x-axis. So in this axis, what do you get? A tau xx. That is one force. So along this x-axis, at this point you have two forces, right? So that is this way. This way, if you say this way, this is your tau y component along this. Okay. What should I say? What is this one? What is your y component? This is your yx, right? Along this, along the x-axis, x component is this, y component is this, perpendicular to this.
Yes, sir.
Followed? Let us say we are at 0 here. We are 0 here, and you will have a delta x. This distance is delta x. So let's take it as by 2. Okay, so together is delta x. So this is delta x by 2. For some reason you will understand. Okay, so delta x by 2 is this one. together. Okay, so delta x by 2 is the distance. This is what is. Similarly, you here what is the force acting here? This is your tau yy. Along the y direction, y is this one, y is this, and then x component is along the x direction. So you'll have x direction, you will have tau xy. X component along the y direction. Okay. And then what happens here? This is the phase this side, right? So this is your tau xx, because this is opposite to this. And what is this one? What is its y component?
Tau
This will
xy.
go this will go like this. This is your tau
Tau xy.
yx.
With negative signs or same sign?
You see, you think of like this. See, this forces, no? This force, tau xx, whatever I'm writing, that is your tau xx. Exactly opposite with a negative sign, no? Negative sign means what? It's a minus. I'm here direction. I'm changing it as a direction. Minus tau xx. That is in this direction. So
Yes,
y
yes.
component here, if you say tau yx is in this direction, then it is opposite. This is going to be opposite here. Okay. Similarly here, this is going to be like this, tau yy, and here this is a negative direction. This direction is your tau y. Do you understand this? See, this you fix it. Let
Yes,
us
sir.
say tau x is in this direction. Tau yx may be in this direction. I'm taking positive y direction. Okay. Y component, x component. Now, obviously, they are perpendicular. They are here. So if it is this, opposite cases, it will be opposite, minus sign. So this is how you are putting it. So if you now, with these things, if you try to calculate, first, you try to calculate your first moment of inertia, and then other things. Okay. First, let's consider moment of inertia. So what is Iz? Now we are actually considering full cube, right? Full cube. So you basically have a cube, okay, fluid element in a cube. That is one phase, okay. So that is basically you have a cube here. So this is that is one phase. So you will try to integrate. So because I have taken 0 to delta x by 2, so this side will be minus delta x by 2 to delta x by 2. That is your dx. Okay. And you are going to integrate. So this is the formula for moment of inertia, right? So the distance r is there. So we will write it. So minus delta y by 2 to delta y by 2. Similarly, another integral minus delta z by 2 into delta z by 2. And here inside, what is that you do? This you integrate. So this is the formula in the calculus if you actually see. So basically what you do is the distance formula that you are going to do. So what is the distance? Inertia, no? So it also will have a mass. Mass inside is basically you bring that rho is there, takes care of dx, dy, dz. And you need to put it as a distance, no? The distance r square. Mr
Yes,
square
sir.
is your mr square is your moment of inertia for a
Yes, sir.
particle. So here r square is simply reference point is 0. So you're doing it for x square plus y square plus z square, right? X square plus only y square. Why is the reason? I'm only looking at the iz component, right? It's only iz component. Okay. So that is basically, this is only for this phase. Okay. Only z component I'm doing now. So only in the xy plane. So fluid element is in the full cube. So when I write z's, no, so
Sir,
basically
only
fluid,
if we consider only IZ, then why 3 integral come? It's not only 2 integral.
moment of inertia, but you are doing for full thing, no? So for the full cube you are doing.
Yes, sir.
When you do the full cube, you calculate these things, x square plus y square, that will give the z component. If you want x component, y square plus z square over the full cube you have to do. You understand? This is only torque in the
Okay,
z direction. Okay. That means you are looking at only forces in the xy plane. That means the one side of the one face of the cube only you are looking at as forces. Then what is this? That inertia, that torque you are calculating for that face only. But when you are calculating this similar way, you are actually calculating Iz means as a formula you have over the full cube. That's an object, no? So moment of inertia means what? It's a particle. Particle is basically 3 dimensions. Here you are thinking that it's very, very infinitely small cube. So that's why you are trying to make it as an integral from small this small to that small. So all that cube in that triple integral m r square. R square is x square plus y square. Yeah, that is for one component. Other component will be y square plus z square. X square plus z square, if you take, that is your ix component. This is the formula for your iz, I think. Right? I think the reason is okay. So no. Yeah. Reference point is in actually in your cube. Okay. But you're calculating only about this face. That is your x-axis, right? Iz is the iz component. Iz means what? Iz is what is Iz?
IZ is
Moment of inertia of the cube, basically.
Yes.
Okay. The full cube only you're doing. Maybe z is there. Okay. Z square, if you take it, I don't think you have a z square. Because you are doing along the z-axis, no? So it only that face only affects, right? Not z. So doing it for finally the delta z. So you're considering only the face. Just look for this moment of inertia. Okay. I think we are only looking at one face only. Finally. Okay. So when we are deriving this F equal to ma, we are looking at only one face. Okay. This is the fluid element, only one face. But when you are calculating the moment of inertia for that phase, okay, you have to put no from 0 to that point. So 0 is here. That point is actually the xy, no? This is xy on this in the xy plane, xy only. So x square plus y square. But why this dx, dy, dz? That's your question, right? Okay.
Yes, sir.
Actually, it is not there. Okay. It is not there. Let's do this. Okay. So when you do, what you get? This calculation you do. This calculation once you do, what is that you do is, what do you get? Can you do this calculation? So you'll get a rho x cube by 3 plus xy square from, you now substitute with x, delta x by 2, delta x by 2. Okay. Still you have integral minus delta x by 2 to delta y by 2 to delta x y by 2. dy is still there. You do one more time, so you'll get finally, I am not going to do this, I think you will get it. So what is that you get here? A rho, let's do, okay? So minus delta y by 2 to delta y by 2. This will be delta x cube by 8, 24, right? Delta x cube by 24 minus of minus delta x cube by 24. Okay? By 3, 1 by 3. That 3 is also taken care actually. Okay? The 2 cube becomes 8, 8 into 3, that is what is 24, 24. Plus this becomes delta x by 2, only x I am putting, so y square into delta x into dy. Is it fine? So this is equal to, this is basically, this is nothing but overall, this is actually delta x cube divided by 12 only. So the 12 like that will come delta x cube. So that becomes that I'm going to write it as delta x square into delta x. Okay. Delta x cube. Finally here delta y comes, no? So delta x, delta y I'm writing outside. Similarly, the other term. So for y square also, if you do the similar way, if you calculate, that becomes delta y square. This is what you will get as your IZ. But you are considering the full cube, I guess. The fluid element is the full cube, F equal to ma. Okay. So moment of inertia of this phase. Okay. So phase by phase, if you calculate. So if you calculate this one, finally, what is that you get? We need to check. So let's write it. Let's write it first, then you try to convince yourself. So this is equal to what is that you get now? What is actually this one? TZ. TZ is rho by 12. This is for the cube. Okay. For the cube, I think we are doing only for the cube. For the cube, full cube, no? Full cube, basically, what you have here is rho by 12 into delta x square plus delta y square into, see, you try to do it for z direction. Okay, so you're basically, when you're doing this moment of inertia, you have a solid body into your hand. That's basically cube. So you are doing only one slice is this one. So how much is that z slice? Basically, you have a minus zx by 2 to that integration. That's what, once you add it, that's what is this z. Okay, this is only for the face. For a face. For a face means what? Divided by iz into delta. For a face, moment of inertia. Okay, so z is it's not along the full z, whatever the full cube. Okay, for the face, moment of inertia for face. So if I really want to put it that way, so moment of inertia for the full cube is basically this thing into delta z. You add here, so that you have a delta z outside. So you'll have a delta z outside. That's what I put it as a triple integral. So this finally you get that one. This is for the full cube only. Okay. So this is the cube, delta x, delta y, delta z. Okay. So now what is that you do? Delta x, delta y. Isn't it? This is what we get, right? Into acceleration. Acceleration, that is, you have a d square theta by dt square. That we have, right? Me, F equal to ma. Where d square theta as it is, I wrote here. This is for the full cube. Okay. So your fluid element is actually in this only. Okay. So fluid element is this, but we are trying to, some kind of approximation. Finally, why we are doing only one phase? Because you do only one phase, and you think that finally you are taking that cube to finally one point, no? So you do work on the slice and try to calculate its rotations. Okay, acting on that. So angular momentum is basically it's a torque in the opposite direction, right? Z direction. You do it for one slice. It is same for all the slices, right? So it is like a dz, delta z, between minus delta z by 2 to z delta z by 2. So that is together, that full slices are together, it is delta z. So this is okay. So that's how you get your torque here. This is the torque for the cube. So what exactly is the torque? The torque is also can be, I can get this Tz also coming from those forces, right? So what is that force that you get? We draw that one, right? So you need to look at that one. You look at this one. This is actually equal to, what is that force? The torque is basically this force into a torque of, let us say, this one.
R
What is that?
cross F, sir. R cross
R,
F.
R into that force, right?
Yeah. Yes, sir.
R cross F. So this force, for example, this ZYX, okay? I mean, tau YX into delta X by 2, okay? If you take this as positive, that is 1. And what happens to this negative one? Net, this is 1. So I'll just write it here. So torque of this phase, let us call this, let me put it as AB. You understand that AB, okay? The torque of AB equal to, so that is of distance from the, with reference to the origin, right? So we'll have delta X by 2 into that force, tau. What is tau? Tau
Tau X, Y.
YX, right? YX.
YX. Yes, sir.
YX.
Because other component
YX.
will be 0.
And if you do effectively, so the opposite, if you look at it, that is going to be minus. Opposite phase to AB. Okay, if you call this CD, let us say AB, that is CD. That will be again minus delta X by 2 into tau. What is the tau? That tau is minus YX, right? So effective will be minus or plus? Yeah, whichever may be bigger, right? So whichever is bigger, so finally you have to take the difference. Why it is difference? I think here also plus only, no? You need to add torque of AB. What is torque? R cross F. And here, what is this? This is your R is what? R is this R cross. This is a negative direction.
Same direction, sir.
Same direction, right? So yeah, it's
Yes,
the
sir.
orientation is same. Orientation is same. So it's a anti-clockwise. Anti-clockwise, if you say this is AB, let us say C comma D. Okay. So if you do this, then same direction. So you'll have to add. So effectively, it's going to be 2 times delta X by 2 tau YX. Now you look at the other phases, right? For example, BC and AC, AD. BC and AD, if you look at it, that is going to be, they are in a different direction, right? You actually see they are different direction. So delta Y by 2, now your tau XY. Tau XY is an opposite direction, so you'll have to take torque in a different direction. So you'll take the minus sign. Minus 2 times effective net will be 2 times delta Y by 2 times tau. What is here? XY, right? XY. Okay. This is equal to basically, this is only considering, is only for that, that's only one slice, right? It's only for one slice. Delta X, what happens to your delta X by 2? How you get your delta Y, delta Z? For the full cube, right? For the full cube, if you actually see, delta Y, delta Z. Where is the delta Y is coming? Delta Y is here. Delta X, delta Z. So that is the distance. And then you actually look at the full cube. Full cube, if you see, that delta Y, delta Z is also there. It is same, no? For each slice, it is same. So that slice is basically this thing. So that is not only delta Z in the 3-dimensional figure, right? So you have see, what we have done here right now here is, for example, only one line only you have taken here. Okay, effective for the full cube, you need to add delta X and delta Z. Okay, delta what is that you have? Sorry, this left side also delta x, no? This is also delta x. Is delta x only, no? This is delta x or delta y?
Delta y, so in for second one
Oh,
is
no,
delta y.
this is delta y. So you
Yes,
have to
sir.
add separately. I think you need to add. This is what is your delta y here and here. So for this is only one line, no? Now once you allow it for full cube, you'll have to add here delta y, delta z. Similarly here, you'll have to add delta y, delta x, delta z. Okay. So what is this one? 2 gets cancelled. So finally you will get tau yx minus tau xy times delta x, delta y, delta z. Okay. So this is separate. Just for your calculation for a line AB, CD. Okay. Only for line AB we are doing. This is one dimension. Okay. So that's why you added delta y for full cube, delta y, delta z into whatever you calculate for a line. Line is like, delta y, delta z directions you'll have. You accounted for full 3-dimensional thing. Now, if you have for normal fluids or external force is only gravitational force, then you don't have any issue here. There is no torque from the gravitational thing. But if you have some magnetic force, ferromagnetic fluids, you may have some external torque due to the external force. Okay. So torque is basically torque per unit volume. That is basically the full volume, right? So that is also if you add that one external thing. Okay. If I'll write it here. So if there is an external torque force, we may add, let's call this simply small tz for the cube. Okay. Small tz into delta x, delta y, delta z, where tz is torque force per unit volume. Per unit volume, you just divide this one. That's what it means. Okay. So that you may have to add here. So that is your just remark. Okay. So that is this is this is the case for certain materials. So what are those materials like ferrohydrodynamics, for example, ferromaterials? Okay, magnetic field, and there is a magnetic field, external magnetic field. So that's called ferromaterials. Hydrodynamics. So this is basically that is external magnetic force creates external torque. You understand? It's just a remark. You just keep it so that we're not adding there. So otherwise you may have to add here. Okay. So here, for example, you may have to add external torque. This is also external torque for the cube, basically for the cube. Now you equate them. This and this, if you equate, what do you get? I'm writing now finally delta x, delta y, delta z, you remove it and you simply get tau yx minus tau xy. Okay, plus that external force, okay, external torque, then it becomes easy, which is 0 in our case. Okay, we assume equal to rho by 12 d square theta by dt square acceleration and your this thing, what happens to your this thing if you remove delta x, delta y, delta z for your what is yeah, here, if you remove your moment of inertia rho by 12 delta x square plus delta y square. Okay, now we are basically allowing finally as delta x, delta y, delta z goes to 0. So what you are getting finally is yx equal to tau xy if tz equal to 0. Otherwise, it is not. Okay, so this is how they are symmetric. Implies the tau matrix is symmetric. When and there is no external magnetic field. Which is the case for our those are the fluids that we consider. Okay, so this is what we do. So basically tau yx equal to tau xy, of course when x is not equal to y. When x equal to y is also same, that is anyway we know, right? So tau x is same as tau xx only. So this is how you see this one. Okay, so now next thing is, what is that you achieved so far? What have we done so far? We have done so far only, we consider fluid element. On that normal you have, on that you have a stress force. I mean stress force, yeah, stress force you will have. It is like a matrix acting on the vector nx, ny, and z, basically n cap. Okay, so that matrix is actually having along the x direction 3 components: tau xx, tau yx, tau zx. Similarly, along the y direction, you have 3 components. So it's like acting as a matrix. This matrix actually symmetric. There is no external torque. That is what is the case for our usual fluids that we have under the external force is only gravitational force. There is no magnetic force, for example, if you don't consider, then it will be symmetric matrix. So you'll have basically so far nothing we've done so far is you have a fluid element. On that fluid element, so for example, you have a fluid element. On this fluid element, you have this n cap. So you'll have a sigma cap, sigma bar, this. Okay, at this point, for example, is your x. So x comma t comma n cap is basically a matrix. We will call it tau time acting on n cap. This is what you achieved. And this is actually symmetric. That matrix is actually symmetric. Now, this is enough for you to just to derive equation of motion, okay, in terms of this stress vectors, okay, so all these stress components, for example, tau xx, tau xy, all these things. Based on this, you can actually derive a moment of equation of motion, okay. So that's what we will do maybe in the next class, equation of motion in terms of components of tau. Actually, you don't say it's a matrix, components of tau. So in terms of, let's write like this, Tij. I and j between 1 and 3. Okay. Any questions here? Please try to understand.
Yes.
We use some basic, I don't know whether it's basic, some of you may not know also. I tried to include maximum the basic physics, that whatever is required. So that that is basically, see, it is not the usual way of looking at it. We generally, students, I know, because I also didn't go through when I was 12th standard. We generally avoid this rotational thing. So angular momentum, angular displacement, angular velocity. I mean, I because anyway, we didn't study. I might have studied that time. I forgot. Okay, so you'll have to physically feel it. When you are rotating, no, that's where you have the angular thing is coming. So angular displacement and angular velocity and angular acceleration. So that same force, this F equal to ma, Newton's second law in this angular rotational dynamics, this will be torque force equal to moment of inertia into acceleration for the cube. We are considering only for the cube. So to calculate the moment of inertia, we only took the one slice. When you do one slice that is in the xy plane, we finally add delta z for the cube. That's why we multiplied delta z. That is same as putting another integral without z square. Okay, we only did for x square plus y square. Rishabh is right that moment of inertia formula is basically m into r square. That m, whatever is in the cube, let us say first put it in the slice, only in the square. Delta x, delta y, only we have written the formula into delta z, but that is basically, this is basically a moment of inertia of the full cube. Okay, so we are considering fluid in the element of a cube. That you calculated. Once you, from that F equal to ma formula, you have a torque, final torque for the cube is that whatever you calculated into that a is dou square theta by dt square, and you directly calculate. Direct calculation tells you, again, another way of looking at it is because of this deformation, for the viscous fluids, you have these forces, no, tau yx, tau xy. So here, what we are considering only those lines, AB and CD. If you calculate for the each line, when you calculate the torque, right? So that is how the delta x, you don't worry. So just to pick up a point from the origin, from the 0, you are looking at the torque of that tau yx. Okay, tau yx, if you calculate, so that if you basically you are doing along this line, each line is one dimensional. Okay, AB, that means y component, tau yx is that one. So that if you do what is the torque, because that is going with reference to this point 0, 0, 0, it is rotating, no, from A to B, it is like a angular momentum. So that's basically, that is the angular displacement is there. That gives you torque. Torque is basically the distance into that force. So that force so you have only for a point you consider. See, you're only dealing with here. Why we are not taking the cross? Because we are only looking at just one point. One point if you do, and finally approximating with the full line. That is your delta x minus delta x, right? So delta y, in fact, right? So for I think we made a small mistake, I guess. So here delta y, right? The delta yx is basically delta y, isn't it? This is delta y, and this is your, if you do it along this one, that is your delta x. Hello? AB means what? AB is moving along delta y. So this is actually delta y. And this is actually opposite face is also delta y. So you put it here effectively, you put it a delta y. This is delta y. Okay, the delta y, and you have delta x here, and this is your delta y, so you'll have delta x, delta z. Okay, and this should be your delta x, so that this is your delta y, delta z. So finally, it's same. You understand what I'm saying? You're trying to. This is actually kind of approximation. Delta y. Don't worry. See, we are doing this AB, right? AB. This is along the y-axis. You're only looking at one point. What is the torque here? So the distance is delta y by 2. This distance is x only, no? Into that force. That force is tau x by 2. I think I'm right. I'm sorry. I think this is the thing, delta x by 2 into, for this line we have done. Yeah, you are right. For this line, that is the delta x only. The delta x by 2, delta x. Sorry. I think I made a mistake. The delta x by 2. This is also delta x by 2. This is, what is this one? This is different. No? This is delta y by 2.
Yes, sir.
Yeah, okay. I'm okay. So this is for the line we are doing. Okay. I think this is, once you have this is delta y, and here delta x. Delta x, delta z for the second one is basically for the other line. Okay. opposite line that we are doing. So here also delta x1, for the line AB, and opposite one we are doing. So this is what? Delta half delta x. So here also half delta x. Because the distance is that one. Okay. So opposite phase is also that one. So finally effective torque will be together, that is this one. Why opposite is also like this? Why this becomes plus? I tell you, distance is basically
It's the same sign because
same
it's
sign. Okay.
yes, yes.
Even if you take 0 to minus this thing, that becomes minus. Yeah, this is basically same orientation. Okay. So torque same direction, so same orientation, that gives the same plus. So you basically get that first component that way. Second one will be between A to C and right, A, B, C, D you have done. So then A to D and B to C, if you calculate, that becomes tau xy. That is similarly, that is the second one. Okay. So this is corresponds to whatever this one corresponds to AD plus BC. This is corresponds to what we have done already, AB plus CD. Okay. So that's how you get this one. So these things, if you equate and finally allow that delta x delta y cube becomes 1 point. So you basically show that it is actually symmetric. So that is what we have done so far. Okay. You have class now?
So we don't have class.
Don't have. Okay. So I can continue a little bit time.
Yes, yes.
It's up to you. Tell me, is it fine? If you so far that's what only we have done. So if there is actually external torque coming from maybe magnetic field that creates some rotations overall full body may get some rotations, some effect, then you may have some torque per unit volume, that if you write it as TZ, external magnetic field. Okay. So that is usually you say ferrohydrodynamics. It's because we're dealing with fluids, right? So that's why we say hydrodynamics. Ferrohydrodynamics may be the case where you have external force that creates external torque. So that if you have, you may not have the symmetry. But usual whatever we do for fluids under this gravitational force, for example, gravitation. Okay. Water, for example. So you have the symmetry. So this is how you get your symmetry. So right now you have this one. So the sigma bar is basically a vector, and you have the stress. This is also stress. This is your stress vector. This is your stress matrix acting on the normal. So it depends on both x, point x, and t and time, and also depends on n. So that's how you get here. So tau actually depending on, so what happens your tau? Tau actually depending on tau equal to tau x comma t basically. Okay. This matrix. Okay. Stress components. Ij will put it here. Stress components. So anything needs to be cleared here?
No, sir. Yeah.
Is it fine? Or you want to just go through it again and I come back tomorrow? Tomorrow we'll have them. You tell me. Otherwise,
Yes,
I'll just our equation of motion we can just derive for this one. Okay. Equation of motion in terms of that's what we'll do maybe next. Okay. So maybe this I'll do it tomorrow. So I'll just leave it here then. Respond. Is it okay? It is okay for me. You just want to understand and come. Yesterday and today, is there any issue? So if you have issues, let me. For example, I have just an opinion that is anyway. I didn't look at that moment of inertia formula. Actually, moment of inertia formula here is in this bracket. The delta z is simply or covering for the full cube. Okay. So actual
Yes,
formula
sir.
is only or applying only for the face. that phase into that approximately, you know, that each phase is the same. So you do it for into delta Z, you're just doing it. So these things you have to understand slowly, everything neatly, so that you will never forget. So it is there in the derivation. So once you understand and keep the derivation, you need not worry about it. Every time just look at it, you will understand. So simply you follow it. Okay. Finally, what you do with this viscous equations is you are going to do only simple. Once you understand this is the equation, that's all. Okay. So you are going to whatever you already derived earlier equation of motion, no? You are going to add only one term. So that one term that involves your viscosity into del square u. That's what you are going to use. Okay. That's your Laplacian operator, no? The del square u. U is your velocity component. Okay, so I think maybe I'll see you tomorrow at the same time, 11 o'clock.
Okay, sir. Thank you.
Yeah. Okay, we go through it, please. Last two, I'm trying to put it in the same file. I'm going to send you again. So go through. So yesterday and today, slowly we'll try to derive the equation. Next, I'll try to derive the equation in terms of these stress components first, and then we will have actually how to relate these stress components to your deformation tensor, that is your strain tensor. Okay, so that is where we assume certain assumptions, Newtonian assumptions. For Newtonian fluid, we assume certain things like stress is proportional to the strain, rate of strain. Okay, and another thing is even if you rotate, you know, rotation, even if you rotate, basically these deformations, that rate of shears, right, deformations won't change much in all directions. Okay, same. Basically what you are saying is basically mu is same for all components. So we will see that isotropic non-Newtonian Newtonian fluids basically means stress is proportional to the rate of strain, and that rate of proportionality constant in all directions is same. Basically, that's what it means. Same constant in all directions. That is what is the, once you assume that as a single assumption, you are done. That is for Newtonian fluid. Non-Newtonian fluid, you may have a different proportionality. Maybe one direction it may be same, other direction may be different. You know, that is where it changes. So we are only deriving it for Newtonian fluid. So Newtonian fluid, this moment of motion, equation of motion, or conservation of momentum equation, these are all the same, no? This is basically your Navier-Stokes equation. Okay. So as such, once you try to understand this small physics, right, how we are deriving these things. Okay. So this is kind of physics, a little bit mathematics, some geometry based on those things we are deriving. So finally, we will get the equation which you're never going to solve it. So you're going to solve only some simpler versions of it that we will see as a Couette flow and Poisson flow. Some little bit flows only we're going to solve it. Otherwise, you should understand these equations as such. These are the set of equations. Equation of mass, you already know that is what works for everything. Equation of moment, for viscous fluids, you will have to add just one term. That's all. Okay. So this is only for incompressible fluids we are doing. For compressible fluids, it may be a little different. So you will see when you derive, you will understand. So where exactly you will have to use that. Okay. So this is, I think, both compressibility, incompressibility. We didn't put the delta U equal to 0. No, that is for incompressible fluid. So no, we are not doing. So this is right now we are doing for full compressible or incompressible viscous fluids. We are right now doing viscous fluid. What is the momentum equation? Okay. And of course, to solve these equations, you need energy equation in this case. In this case, you need really energy equation. So that we derive in the general case using the Reynolds transportation energy. Okay, that's we call the energy equation. Okay, so conservation of energy. Those three equations in principle will solve all the unknowns in the equations of those partial differential equations. That basically, in principle, you will get the number of equations equal to number of unknowns. In principle, you will solve, but you don't know how to solve it. Okay. The simplest cases, we'll try to look at one or two, and we'll try to see how we generally non-dimensionalize, how we derive certain Reynolds number, some non-dimensional parameters in this equation, and we'll see those. So Based on that parameter, that is called Reynolds number, we can see what kind of flow you can expect physically. So that's what we'll see. So before that, we'll have to derive this equation. So try to understand slowly so that you'll never forget. Okay? Okay.
Okay, sir.
Yeah, I'll see you maybe tomorrow. We'll derive first this equation of motion in terms of stress components first. Then we will see those stress components in terms of this deformations, right? Those are strain. Strain means basically in terms of your velocity vectors, u bar. That is where actual equation comes. Okay, so we'll see tomorrow. Bye.
Okay, sir. Thank you, sir.
Yeah, see. Bye.